Hello, I'll go over this problem. Two sliders or two collars on two rods connected by a cable. Collar A and B are connected by a 25-inch long wire and can slide freely on frictionless rods. If a 60-pound force Q is applied to collar B as shown, find tension in the wire when X is given and the magnitude of force P that is required to maintain the equilibrium of a system. So this is an equilibrium problem. And in statics, usually when we have equilibrium, it's either a rigid body or it could be treated as a particle. In this case, we can look at point A and point B and see that we have two particles, or we can consider two particles. So we'll treat this as a equilibrium of particle problem, and we'll draw two free body diagrams. Each of them is for a particle. So let's start with the free body diagram. Remember, there were three steps for a free body diagram. Step one is isolate. Whatever you are trying to draw the free body diagram, you isolate and draw the outline of it. Step two is add all the active forces. Active forces are forces that are trying to disturb the equilibrium. External forces, external moments, stuff like that. And step three is to add all the reactive forces. Reactive forces are forces or loadings, could be forces, could be moments, that are created as a result of active loading, active forces and active moments being on a system. So let's just start with that. And we'll start with particle A. So FBD of particle A. Step one, isolate. That means remove all everything else that we don't need except for the particle and draw the outline. You can draw the outline of the color, or I'm just going to put a dot here. Okay, that's my particle A. So that's step one done. Let me just add those axes here. All we care about is the direction. Doesn't matter if point A is not at the origin, point O. All right, that's my particle A. Step two is add active forces. Active forces that I see is force P pointing in the direction, same direction as positive x-axis. So I'm going to add point P acting on my particle, force P, sorry, acting on my particle, pointing towards positive x-axis. Some people might consider the tension in the cable as an active or reactive. Doesn't really matter how you want to do it. In any case, we have to add it next. So the tension, I always draw tension as going away from the point. That's indicating a tension or tensile force acting on a point. So starting from point A, going away in the direction of A, B. Tension A, B, going from A to B. Another reactive force that or forces that we're going to have is reaction created by having the tension and force P that's created by the rod and the collar or the slider. In this case, it's going to have a normal force in X direction, normal force in Y direction, and normal force in Z direction. But this slider can move freely back and forth in X direction, so X is not going to have a reaction. But Y direction and Z direction, they're still going to have a reactive force created at that at point A. So I'm going to put a, let's call it N for normal force, N in the direction of Y, and an N force in the direction of Z. All right. I don't think there's anything else I need to draw. So let's move on to particle B. Have my axes here. Step 1, isolate, draw outline. You know, for this one, let's just draw it like this to show that, hey, you can draw either way. So that's my particle B. Next thing is add active forces. Again, same as before. I'm going to add Q, which in this case, it's given as 60 pounds. I still have the tension. Again, it needs to go away in the direction of B to A, kind of approximately having it this way. Call it BA. Same as before, we're going to have reactive forces created between the collar and the slider. There's going to be 3 forces, one in the direction of Z, one in the direction of X, one in the direction of Y. But I can see it can freely go back and forth on Z. As a result, there won't be any reaction. There is no need for the slider or for the collar to have a reaction in that Z direction, because it can move freely. Every time anything can move freely or rotate freely in a direction, there won't be any reactive forces or reactive moments in that direction. So we're going to have a normal force. Let's not call it N again. Let's call it R for reaction or reactive. We are going to have an Rx and we are going to have an Ry. Okay, so we have 2 particles and we have a lot of unknowns. There's a lot of unknowns. The only thing we know is Q. Everything else is unknown. P, N's, tensions are all unknowns, but we can solve this problem. So let's take it one step at a time. Let me add here, this is FBD of B. Okay, so this is our free body diagram. I'm going to bring it back. Let's work on our tension a little bit and kind of define this tension, which these two are equal magnitude wise. They're opposite direction but equal magnitude. So let's find out and define T in vector form. So let's clear this up. My goal is to write T AB or BA, doesn't matter, as a vector in this case. A vector is defined by a magnitude. I'm not going to put the arrow on top. That means it's a magnitude multiplied by, or I shouldn't say multiple, but magnitude next to unit vector of A, B. So okay, remember this is unit vector. And this is magnitude of T, magnitude of tension, or TAB. And this is TAB in vector form. This is a vector, magnitude is a scalar, and unit vector is a vector. Okay, one side I have vector, the other side I have vector. Unit vector of A to B is defined by position vector AB divided by magnitude of position vector of AB. So this is position vector from A to B. This is magnitude of position vector from A to B, which in this case is also same as length of the rope or cable, whatever the problem called it. Let's look back quickly. 25-inch long wire. Sorry, it was a wire. So the magnitude in this case is 25 inches. Okay. no arrows. This is a scalar. This is only the length of AB 25 inches. So, and remember, we create a quick table here to keep track of points and their coordinates. X, Y, Z units. A is located at X, which the problem gave us 9 inches right there. So I'm just going to write 9 inches. Located at Y of 20 and Z of 0. It's on XY plane. Point B, I'm going to go a little bit quicker. Located at X of 0, Y of 0, and Z of Z. We don't know how much it is. And units in both cases are inches. All right, let's write position vector AB. Position vector RAB. Remember, B subtracts A from B. Coordinates B from, B from A. Or no. A from, subtract A from B. There we go. Sorry about that. So that means 0 minus 9. This is going to be I. 0 minus 20. This is going to be J. Z minus 0. This is going to be K. Units of inches. If I want to write BA, subtract the other way. So it's going to be 9 minus 0, I, 20 minus 0, J, 0 minus Z, K. Same in inches. All right, now let's go back and create that unit vector AB. So unit vector AB, 9 over 25, I, 20 over 25, J, Z over 25, K. There's no units because these are inches divided by inches, so that there's no units for unit vector. But let's find Z. Remember, magnitude of unit vector, any unit vector, magnitude is 1. That's why it's called a unit vector, because it has a magnitude of 1, and all it does for us is adds a direction. So 9 over 25 squared plus 20 over 25 squared plus Z over 25 squared, this should be 1. As a result, if you do the math, we're going to get Z equals to 12 inches. Okay. All right, let's go back to our free body diagrams and figure out unknowns and what we have to do. So I redraw the free body diagrams here. Next, what we're going to do is we're going to use equations of equilibrium. So for equilibrium problems, step 1 is drawing free body diagram. Step 2 is equations of equilibrium. That's it. Why do I call it equations of equilibrium? Because this is a vector. This means summation of forces in X equals 0, summation of forces in Y equals 0, summation of forces in Z equals 0. This is a particle, so we only need to consider summation of forces. And this is a vector form, this is in vector format, and it has 3 equations. So let's just start with the one that we have more known quantities, because particle A, we don't know anything about it. Particle B, we at least have Q. Okay, so let's write for particle B. I'm going to write summation of which way is Q in Z. So I'm going to write summation of forces in Z equals 0. That's good because then I don't need to worry about Rx and Ry. I don't have to consider those. I have Q pointing in positive z, so that's positive 60 pounds. The only other thing that I need to consider is a z component of vector t, which again from previous slide I have t BA, this is magnitude in vector format if I want to write it. It's going to be minus 9, well this is BA, so it's 9 over 25I 20 over 25J minus Z, which was 12 inches over 25K. Okay, the only thing I need to consider in Z direction is the Z components of it. So it's 60 minus T BA 12 over 25. This is inches equals 0. If you do the math, you get TBA, which is same as TAB. The magnitudes are the same, 125 pounds. Okay, so I know the magnitude here, 125, and let's move on to particle A. And P is in x direction, so let's just write out my equation of equilibrium in x direction equal to 0. Then I don't have to worry about ny or nz. I have P that is positive in this case. The way I drew it, well, the way the problem gave us, positive P, and all I have to consider is the x component of AB. Remember, AB and BA, they have the opposite direction. So that one is going to be minus 9 over 25, sorry, T AB, 9 over 25 inches equals 0. I already know T is 125 pounds. So let me write it a little bit cleaner here. Minus 125 pounds, 9 over 25 inches equals 0. This should result in, if my math is correct, 45 pounds.